NA issues. Okay, quick recap. So the numerical aperture for any optical system is all to do with the maximum cone of light that can get into it. So imagine a source of light, a certain distance, guess where I'm imaging, and a cone is produced and it's captured by my optical system. Then the numerical aperture is defined to be n sine theta. Okay, and it's related. It's many things associated with the numerical aperture, but for now let's just think about it as the cone of this angle. So one example about this might be, say, optic fibers. So optic fibers have a particular core, and they have a particular relationship between the refractive index of the cladding and the core, and the result of this is that they have a maximum acceptance angle that they can accept. And so therefore, a fiber itself has its own, say, numerical aperture, say 0.2. And that would be, if n was air, then that would be the sine of the angle, the maximum angle of incidence that a beam can come in at. And that would be about 0.2 radians, since it's very small. And since 1 radian is 60 degrees, 0.1 is about 6 degrees. So that's about 12 degrees, about 10 degrees inclination. So in other words, it would be the steepest ray would be sort of something quite shallow. So it's quite shallow. Right. Okay, but also given the fact that we know that light's going to be, you can imagine light to be a series of plane waves traveling in that direction of a particular wavelength. In other words, of a particular k, the angles travelled per meter, and this is constant. This is given by my wavelength in a vacuum. Since this is the case, it will mean that there's a particular x component. So kx over k nothing is the same as sine theta must be the same as my numerical aperture over n. So, and also that's the same as lambda naught over lambda x. So lambda would be the distance between the peaks, and lambda x, as we mentioned before, is the spatial frequency in the x direction. So therefore, I can clearly see that's equal to Na over n, that my spatial frequency is in the x direction is my original divided by whatever the Na is. So this would be the highest spatial frequency that can be captured. In other words, the smallest wavelength. So the bigger Na is, then the greater, the smaller the wavelength is, the spatial frequency that can be captured. So if I've got the core of a fiber like this and I project, say, a Young slits pattern on it, then if my Young slits pattern is smaller than this cutoff, then it can't get through, can't be accepted, because it means, imagine my Young slits pattern is made up by, I don't know, a horizontal beam like that, and then a diagonal beam like this, because it would mean that this it would not get through because the inclined beam would not get through. So in other words, it provides a hard limit. I can see clearly what the limit is of my spatial resolution.